Good morning, good afternoon, and good evening to you, my dear viewer. My name is Julian Kreusser, here today with the Foundry, bringing you the second part of our two-part tutorial series on depth maps. In the first part, we looked at generating some depth maps that are super detailed, temporally consistent, and matched with a camera track. We did that using MiDaS. Now here in the second part, we're going to learn about some really cool use cases for that depth map, including using it to relight a scene. So if you think that sounds interesting, you'd like to follow along, all the resources you'll need are in the description. And without any further ado, let's get right into the tutorial. So here we are back in Nuke, right where we left off in the last part. And since then, I've gone ahead and rendered out our depth map before it goes into this color transfer here, so the B pipe. And this is just so we can have the speed of a pre-rendered depth map with the control of being able to, adjust our camera up here and all of that in case we need to. So now that we've got our depth map all sorted out here, got that taken care of, what can we do with it? Let's take a look at 3 quick examples of some cool things you can do, and then we'll get into the main event, which is using this depth map to relight a scene. So I'm going to go ahead and bring down our footage as in a separate little pipe here, so that we can use both of these, the footage and the depth, next to each other. And I'm just using the period key to bring up these little dots for organization. So you can see here, I've got my depth map and the original plate. So the first thing we're going to do is try and add some fog to this image. And that is going to be mainly accomplished with a grade node. So G for grade, there it is. And I'm popping this down onto the footage. And you can see if I adjust it right now, well, we're adjusting the whole image. And with the way that fog looks, we want to disproportionately adjust further areas in the image. So we're going to use our handy dandy depth map as a mask. And I can just pop that in here right on the mask input. And this way it's going to affect areas that are brighter in the depth map more than darker areas. And right now you'll see non-existent channel used for mask. And that's because by default it expects an alpha channel mask. And this depth map is just in the RGB layers. So I'm going to go into the grade node here, right next to where it says mask. I can choose one of the RGB channels instead of the alpha channel. And now you can see, well, if I do something like an offset here, it looks like it's affecting the foreground proportionately more than the background. And so since that's the opposite of what we want, I'm going to check this little invert switch. And now looks like we're getting the background here mainly. But the fall off is pretty short here. And so if we want to adjust that, what I can do is pop a grade node on the depth map and then go ahead and adjust the range to where we want it to be. Adjust the black point and the white point. And it's probably a good idea to turn on white clamp as well. The grade node here only expects 0 to 1 in the mask input. We can also adjust the gamma, get the fall if we want. And then in order to get a proper fog look, what I really want is to increase the offset and also bring down the gain, because some of the light gets lost in the fog. And with that, it looks like we've got our fog happening. So here is a before, after, and you can see it's looking pretty good. And here it is in motion. You can see that it still works absolutely fine. So that is our first cool thing that you can do with depth maps. And I'm just going to pop this over to the side here, add a couple more pipes, holding down Control here on the keyboard, by the way, to do that rerouting thing. And I'm going to make a little backdrop here so we stay organized. Ooh, white color for fog. And the second thing that I want to look at is, well, we notice that we've got some pretty sharp lines up here on the edge of our character in this fog trick that we did. So maybe we can use this depth map to extract a matte of our character. I think that would be pretty cool. So this is going to be pretty similar, but since we're working with a matte strictly this time, I'm actually going to first shuffle our depth map into the alpha channel. So red goes into alpha, and now if I hit A to toggle to the alpha view, there it is. But as I mentioned before, we really don't want any values over 1 for our alpha channel. So I'm going to bring in a grade node, set the channel to alpha, turn on white clamp. Now we're maxed out at a value of 1, and we can adjust the white point. I want to bring in all of our character and then turn up the black point until we're excluding the background. And let's see what happens if we now copy this over to our alpha channel on the footage. That's K for copy to bring that up. And then if I go ahead and hit M to preview the mask, you'll see we have a pretty nice outline of our character. And if I go ahead and pre-multiply this with the pre-mult node, there it is, background removed. And just to illustrate what this is actually doing, I'm going to merge this back over the original plate. And then in between the plate and this merge, I can add anything I want in the background. So I'm going to do a quick roto here with the output in RGBA. And we can see we've got this mystery cloud shape behind our character. And this is looking pretty good, but our lines on the edge are a little bit simplistic. They are not exactly very detailed. And for that, well, how about we use RS guided blur, that node that we used over here for an unintended purpose for its actual intended purpose, which is to clean up matte edges. So I'm just going to paste this down here and connect both inputs to this copy node here. This is going to let us adjust our matte before it goes into the pre-mult. If I bring down the blur size to something around 7 for this case, you can see we've got much improved edge detail here on our character. And so this is our second cool thing that we can do. This one is going to be matte extraction. So I'm going to bring in a backdrop. We'll name this one for organization mattes. There we go. And finally, I want to look at one more cool thing that we can do. So once again, bringing over the footage and the depth, and this one is dead simple. I'm just going to bring in a copy node here. Once again, we don't have an alpha channel here, so I'm just going to copy the red into the depth.z channel. And now, if I bring up a z defocus node, it will just automatically work. If I can put the focal point on the character here, you'll see the background and foreground are a little bit softer than they were before. And just to exacerbate that effect so that you can see it better, I'm going to turn up the maximum size to 30 and the size to 15. And then there you go. You can really see what we've got going on here. The background is all defocused. It looks like almost a tilt shift setup or something like that. And this is really cool. You can actually adjust the focus of a clip after it was shot, which I think is super neat. Of course, it's not going to help bring something that was already out of focus into focus, but it will help if you want to get some exaggerated focus effects. Yes, check that out. So there it is in motion. You can see it still works great. And this is giving us our first hint that these depth values that we've got are actually real 3D values that we can use for this next part here. So let me just put a backdrop around this for organization. We'll call this one defocus. And now we can get on to our main event, which is using our depth map to relight this shot. Bring in some new 3D interactive lighting. So how can we accomplish this? Well, the main technique is this. We're going to use this depth map to extrude some 3D geometry out to fit the shape of the scene. Then we'll light that and apply that lighting map to the original footage. And if that doesn't make sense quite yet, it will. Let's just follow along. We'll figure it out together. So first things first, if we want to turn our depth map into some geometry that we can light, we're going to need some geometry to start with. So I'm going to go ahead and bring in a card. I'm going to hook up its image to our plate just so that we can see. And then if I go ahead and hit tab to bring in our 3D viewport, you can see that our card is right here with the footage overlaid on it. So we've got something to work with here. But you can see that it is very much not in the shape of the scene. It's completely flat, in fact. So how can we use our depth map to change the shape of this card? Well, we've got a node just for that. It's called Displace Geo. So I can go ahead and connect that up to the card and connect the displace input up to the depth map. And ooh, that is a start indeed. You can see the floor is coming towards us a bit, and there's even a little bump for the character. The back wall stays about the same. So this is a great start, but if you ask me, it's not looking exactly how we want it to at this point. I would imagine that in real life, the floor wasn't on a slant like this, and the room was probably a little bit deeper than this. So for one thing, let's try just turning up the scale on the displaced geo. You can see right now it's at 0.1. And ooh, this is looking more like it, but I think that his head probably wasn't shaped like this in real life, and that's happening because our resolution on the card is so low. You can see there's only so many points that we have here to represent the scene, and to increase that, I'm going to go down here to the card, and where it says rows/columns, I want to make this, I want to increase this, but I want to keep it the same aspect ratio as our clip. So you'll see we have our resolution is 2048 by 1080. I could just make it 2048 by 1080 rows and columns, but that would be really slow to work with. And so I'm just going to divide that by 10 and do 204 by 108. You see already, ooh, hey, this is looking a lot better. Now we've got the character as pretty much a separate object in the scene. It looks like you can see he's got his own defined edges, although they are a little bit blocky. So I can just go in here and type *2, and that's going to multiply this by 2. And now, all right, well, we've got a little bit more geometry to work with. The edge is looking a little better. So now that we've got enough resolution to properly represent our scene, let's get back to making it actually fit the proper shape of the scene. And I can immediately see a glaring issue here, which is that the distribution seems to be incorrect. If we were to trust what the geometry is saying here, we would say, oh, well, it looks like our character is much closer to the back wall than he is to the camera, or the front of the scene. And if we look with our eyes at the plate, we'll see that that looks like it isn't true. It looks like he should be much closer to the camera than he is to the back wall, but the geometry begs to differ. So what's the confusion here? The issue is that our depth map is in reciprocal encoding, and it should be in linear encoding. And what I mean by that is that a depth map should represent the distance from the camera on each pixel. And if we were to directly represent the distance from the camera on each pixel, that would be a linear encoding. And what that would look like here in a sort of abstract representation is this. This is a linear function. It means that if we go in with a depth value of 4, the value that will be stored in the depth map is 4. And it's the same for any value. You put in 8, you get 8 out. But that's not what we're doing here. We're actually using 1 over the distance from the camera. So this is what's being stored in our depth map, and it's a completely different shape. And you can see that it just so happens that that is the default way to store depth in Nuke. If you look at the ZDFocus node here and you hover over where it says math, you can see that far equals 0, which is the default value, is 1 over distance. And that's what we use in Nuke and apparently RenderMan. But that's why the example that we did with ZDFocus over here just worked so well, is because we had already set it up to be in that reciprocal encoding inadvertently. But anyway, the point is that we need to get this back to linear encoding, because look, you can see this looks like our Desmos graph in a way. All of the higher depth inputs are getting squished down into a smaller area of outputs, whereas the closer values are getting expanded up further. And that's exactly what we're seeing here. All of the back wall and our character are sort of being squished down, whereas the foreground is getting extended out. So let's put this back into linear encoding. And an easy way to do that is just with an expression node, because all we need to do to turn this reciprocal encoding back into its linear counterpart is just to take the reciprocal again. You can see if I do this, divide this whole thing by 1, we get back to the linear encoding. Anyways, we just have to do that here. And that is as easy as just doing 1 divided by the red channel. And I'm making this a variable. We'll call this variable D. And then I'll put this variable into our red, green, and blue channels. And if I plug this expression in, you'll see now we are getting a more realistic distribution. You'll see our character is much closer to the front of the scene and much further from the back of the scene. And you'll also notice, we have some pretty crazy values in the back of the scene. And if I step sort of between frames here, you'll see that they vary quite a bit. Like, that is a pretty significant jump from those pieces that are out the window here. And this happens because of a quirk with this reciprocal encoding. If I go in here and just add a little bit of noise to our reciprocal function like this, you can see it looks pretty insignificant. It looks like a small amount. But then when we go to invert it, take the reciprocal again to turn it into linear depth, this happens. All of the further values, everything gets expanded, blown back up, and so does the noise. So the noise is going to be disproportionately large for further values as opposed to closer values. And that's just an unfortunate truth. There's not really a way to get around it that I know of, but you can see the foreground values much less noisy. Anyway, all that is to say, it was important that we did the denoising in the first part, so good on us. I digress. We'll get back to this now. You can see it still doesn't look quite realistic. The floor probably shouldn't slope like this. And, you know, if we look at it from the front, it still doesn't look like it matches up with our clip. Like, for one thing, it's flipped, but the background seems way too small compared to the foreground. So what remains? Well, we can actually get a pretty good hint from just the regular old camera node. If we look at it in the 3D space here, you can see that it's got this shape coming out of the front of it. It sort of looks like a four-sided pyramid. And that shape is called the frustum. What it represents is that everything inside this shape the camera can see. Everything outside the camera cannot see. And this is the reason why we have perspective in the camera. You'll notice if I just bring in like a little sphere here or something, it takes up a much larger area of that frustum shape when it's close to the camera than it does when it's far away. So we would expect our geometry over here that we have, that is captured by a real life perspective camera, to have that same triangle pyramid frustum shape, right? Because everything that the camera can see will fall within that sort of shape. So there must be something wrong because we have a rectangle shape here. So what gives here? How can we fix that? Well, this is happening because our displaced geo is only moving the vertices in one direction. It is moving them on the z-axis exclusively. And if each pixel in the depth map is representing distance from the camera, it should expand outwards, getting bigger as it gets further away from the camera. But in order to do that, we would need to be able to have control over all three directions, X, Y, and Z. And it looks like our displaced geo node can only go in one direction, right? Wrong. There actually is a secret option for it under the source setting here. By default, it's on luminance. You can also choose red, green, blue, or alpha, but these 5 options all pretty much do the same thing. They just let you control movement in one direction. The last 2 on here are special because RGB absolute, RGB relative lets you specify an X, Y, and Z coordinate with the red, green, and blue channels. So 3 values in, 3 values out. This is exactly what we need. But you can see if I select it, immediately our whole thing just disappears. And this is because currently all 3 of our X, Y, and Z coordinates are the same thing. And so it turns into this big line that goes off into space. So first, we know this is what we need. This setting is what we need in order to proceed, but let's just try and get back to where we were before with this setting on. So we're looking at our depth map, which is now going to have to become a position map, meaning each pixel represents a coordinate position. And well, right now it's still a depth map, so how can we turn it into a position map? Well, we can pretty much ignore our blue channel for now. It's all good. That's our Z channel. It's just the depth, so that should be fine. But the R and the G, the red and the green, are going to need to be something else. In the expression node, we have some built-in variables for X and Y. these represent our pixel coordinates. And so you can see if you look down at the color picker down there, you'll see the red and green values directly correspond with the x and the y coordinate. And so this should work to sort of, distribute the geometry over an area, but the problem is that this is going to be a huge, huge area. It's going to be at the top right corner, 2048 by 1080 units big, which is huge. And so what I can do quickly is just normalize these values, put them within a 0 to 1 range by dividing by the width on the red and dividing by the height on the green. And so if we just look at our red channel, it's going to go from 0 to 1 this way. On our green channel, it's going to go from 0 to 1 this way. And what this looks like in our 3D viewport is this. There we go. Okay, so we're getting closer to where we were before. However, you can see it's now all square shaped because once again, we've got normalized coordinates going from 0 to 1, 0 to 1. But before we put this back into the proper aspect ratio, it's going to be useful to center it. And that's easy to do here by just subtracting 0.5 from both of our coordinates. That puts it in the center. And then in order to get back to our original aspect ratio, we're going to want to put some parentheses around both of these expressions to get the order of operations right, and then multiply this y-coordinate expression by the height divided by the width. And that should put us back into our original state that we were in before, but now we've got control over all three coordinates. So what can we do in order to make the geometry expand outwards the further it gets away and sort of contract inwards the closer it is? Well, we've already got the depth value, which gets bigger the further something is away and gets smaller the closer it is. So maybe, if I'm lucky here, I can just multiply times d on both of these. And there we have it. Look, you can see that frustum shape emerging. There's that sort of triangle shape that we're looking for, and this is already looking a lot better. But one quick thing here, you'll notice if we switch between the geometry and our original plate, you can see looking a lot closer, but it is flipped still. And also, if we look in the 3D scene and compare where it is with our camera, it's going in the opposite direction. So an easy way to get both of those in one go is to just invert, put a minus sign before the depth in our Z channel, our blue channel, and that way it's going the right way. See, this is getting very, very close. Look at that. We've got the geometry in a frustum shape, and it's in front of the camera. And so our gold standard here is going to be, if we look through our camera that we got from our camera tracker, it should look exactly the same as the original clip. And if we do that, then we know that we've succeeded in recreating the scene geometry. So let's have a look. I'm going to bring in a scanline render, and I'm going to plug in this displaced geo as our geometry, our object, and then plug in our camera tracker camera as the camera. If I look here, you'll see, unfortunately, this does not look like the original clip. So what can we do? This doesn't look correct. It's bigger, and it also seems to be slightly rotated, oddly. And the perspective, there's a subtle perspective shift here, which is a little bit hard to spot, but it exists. So what gives? Well, if you think about it, what we're doing here is, with this expression and this displaced geo, is that we're assuming that the camera is right at 0, 0, 0 in our world. It's at the center of our world, and so we're projecting our geometry from that spot. But the actual camera at this point has moved. And so in order to make it fit properly with our camera track camera, we're going to need to move the geometry in order to have it follow the camera. So since this pipe up here is connected to the camera, I'm going to place down a dot, and then I can use a transform geo node with this camera as the axis. And with that, we should see that the geometry, especially if we look here at the front of the scene, the geometry will follow where the camera is. And this is going to help some. If I look at the output of the render, you can see now the perspective has been corrected. You don't see those jaggedy lines on the edge of the arm. However, we are still zoomed in too far. And what is up with this? Well, maybe if I were to go up into the camera and adjust the focal length, I could try and zoom it back out to get it to fit. You'll notice here, when the focal length matches the horizontal aperture, then in that case, it actually does match up perfectly with the original clip. But we don't want to adjust the camera's information, the camera's data. We want to adjust our geometry to fit where the camera is, because we assume that this is the correct value. We want to make it physically accurate. So we noticed that when the focal length and the horizontal aperture were the same, that's when it looked realistic. So perhaps we can work these two values into our expression somehow to compensate. I'm going to open my expression node back up, and then I'll make a new variable here called h. And I will hold down Control and drag the focal length up. Go ahead and delete this Nuke knob part because we don't need that. And then I will drag up the horizontal aperture. And I'm just going to try dividing one by the other and then multiplying the x and y by that. And that seems like it's gotten bigger, so maybe we try the other way here. And there it is. That was the last little bit of math that we needed to do. And with that, you can see that our output from the scanline render and our original plate looks just about the same, with the exception of some little aliasing around the edges, but the placement looks totally correct. So just to recap all that math, because I know it was quite a bit, here's how we turned our depth map into a position map. The red, green, and blue channels correspond to x, y, z coordinates when you're in RGB absolute mode in Displace Geo. So we'll use the x and y pixel coordinate variables in our red and green channels to spread the geometry over a 2D area. However, this area is huge and will vary with footage size, so dividing by the width and height variables allow us to normalize the values, putting them between 0 and 1. To make future scaling easier, we subtract 0.5 from the red and green channels to center the geometry in space. We multiply the green channel by the inverse aspect ratio to squish the geometry back into the shape of the footage while preserving the width of 1 unit, which will be important later. For the blue channel, which represents the z-coordinate, we'll use the values from our depth map, in this case pulled from our incoming red channel. But we've got to make sure to take its reciprocal to put it back into linear encoding, where the values directly correspond to the distance from the camera. We'll put that into a variable d so we don't have to keep typing it out. Since taking that reciprocal flips the value distribution, we'll negate the blue channel so we're facing the right direction again. In order to fit the geometry into the scene camera's frustum, we multiply the red and green channels by the depth, which scales the geometry based on the distance from the camera. This is necessary because all points with the same distance from the camera fall on a sphere, and a given area of that sphere will grow as the distance increases. So area needs to scale with distance. Basically, we need to project our geometry outwards from where the camera is, not forwards. Next, we multiply the red and green channels by the ratio of the camera's horizontal aperture to its focal length. This ratio tells us how wide the camera's field of view is, and lets us scale our geometry to fit within it. This convenient bit of math only works because we kept our width at 1 unit earlier. Finally, we use a transform geo to parent the geometry to the camera. Since the depth map was relative to the camera to begin with, this cancels out that movement and leaves us with stationary scene geometry. So that was the recap. Now let's get back to the tutorial. And this is super cool. This is what we've been after this whole time. Now we have scene geometry that's actually tied down to these physical points that we got from the camera tracker. And we even have depth for our character, which is, once again, a moving thing in the scene. We couldn't get this from the camera tracker. But anyway, now that we've got our geometry recreated in the scene, how cool is that? How do we use this to relight? Well, given that this is all a 3D scene here, and we've already got our texture applied to the geometry, it should be as easy as just putting a light into the scene and letting the renderer take care of the rest. So I'm just going to put down a light, add a scene as well, and we'll make sure that both our scene geometry and our light are connected to this. So they're both hooking into the render. And you'll see, well, for one thing, this light is ginormous, and so I'm going to bring down the scale so it's a little bit easier to work with. And then if I just go ahead and position this in our scene, we can tap into the 2D viewport and see that we're getting a kind of yucky looking result, which we can make a little bit better by changing the fall off type on the light to linear. And you'll see, well, here it is. Here's the relighting in action. And yeah, it's completely interactive. We can move the light around and we get this sort of dynamic shading on our character. I think that's pretty cool. And we've got the, splash of light on the ground and all that. We can even move it further back in Z space and see the scene being lit from different angles, even having that edge lighting and everything. And of course, if I do a quick play blast on this, we can see that it still works in motion. And you'll even notice that the spot on the ground, which the light is above, is staying fixed in 3D space. It's tracking with the scene because our depth map is based on that camera track. Of course, I'm not sure I would call this a passable look. And so let's see what we can do to make this a little bit better. There's a few issues that I'm noticing here. For one, the shading looks too high contrast and it's pretty visible, these jagged edges that we're getting from the low resolution geometry. There's also still a decent bit of flickering going on. So let's take this one step at a time and see what we can do to help make this look a little better. So let's first take a look at seeing if we can clean up these edges a little bit to make it look a little bit less nasty. And in order to do that, we're going to, instead of rendering the image directly affected by the 3D render and by the light, we're going to render a light map and apply that to the original clip. And so what that looks like is this. I'm going to unhook the image from the card input. Now it's no texture on it, so it's completely black, and I'm going to hook in a diffuse shader instead. So if I hook that up like this, you'll see that now we just get a black and white image describing the brightness across the render. And then I can just use a merge node set to the multiply method to merge the output of our 3D render here and the original clip. And once I do that, you'll see the result is the same thing that we had a second ago, but now we can independently modify the light map before it gets applied to the clip. So for example, I could do something like blurring it, and this will make the shadows look a little bit nicer, but you'll see when we still get that little haloing effect around the edge. And so why not use one of our best friends? Once again, we'll bring back RS guided blur in order to adjust the light map before it gets applied to the clip. So I'm going to paste this down here. And remember, since we are trying to modify the shape of the light map, we'll need to plug it in as the matte input. But of course, it's going to be expecting a matte because that's what it's designed for. So we'll need to pass this in through the alpha channel. And in order to do that, we'll use a shuffle, put that here, and shuffle red channel into alpha. And now you can see there it is in the alpha channel. And switching over to the guided blur node, now you'll see we'll get an evenly blurry image, and that's because we need to connect our image input. And as soon as we do that, well, now we've got something interesting going on for sure. So if I go ahead and shuffle this back into the RGB channels instead of the alpha channel, and then go ahead and multiply by this resulting image instead of just the direct render, you'll see we get a pretty strange looking result. And that is because our blur size is cranked up super high. So if I bring that down to something more reasonable, you can see we're getting a similar effect to that blur, but without as much haloing going on. And so this is, I would say, an improvement from this. It's looking a little bit nicer, but still not entirely great. So what else can we do? Well, for one thing, it's a little easier to hide the flaws that we're getting if there's not so much contrast. And so instead of making it so that our light map is taking the image down to 0 in the dark spots, let's just make it so that it leaves it at the original value in the dark spots and boosts up the bright spots to be brighter. We can do that by just grading our resulting light map and offsetting it by 1. So this way you can see what it's doing is just brightening up the spots that we want to be brighter and leaving everything else the same. Of course, with the guided blur, it's important to notice, oh, we've got some weird stuff happening around the edges here. What's up with that? Well, it turns out that we have a little 1 pixel gap in our render. It's always these little things that'll come back and get you, but it's easy enough to repair this. All we got to do is put a crop after our render, either before or after the shuffle, it doesn't really matter. And then I can just go ahead and hold down Control and adjust this crop bounding box so that it is slightly just cropping off that edge pixel. And then if I uncheck black outside, it's just going to extend that out towards the edge. And now we should see in our resulting thing, we have no more of those weird edge artifacts. So this is looking better, to be sure, but the effect isn't so pronounced anymore. And so in order to make this look more visually interesting and to, really just achieve more of an effect, I'm going to go into this grade here and boost it up. I'm also going to use the multiply setting down here to slightly shift it over towards orange, because I think that is a cool looking result. And then to make the resulting image look even nicer, I'm going to grade the output of this, bring down the gamma, and bring down the gain as well. There we go. So this is looking much more interesting than what we had before, and you can see it still retains all of that interactivity. So if I move the light over here, we've got some brand new light in the scene. It's all interactive and everything. You can move it up, put it in front. It's all very cool. And of course the light stays tracked in position as it did before. Let's have a look at what this looks like now in motion. I'm going to do another flip book here. And there we go. That is looking a lot better than it was a second ago. In fact, I think this looks pretty darn good. But there is still a couple little things that we could clean up. You can kind of see a little ghost of brightness around his head here. And I don't know, I think it would be cool to have a bit more of a dynamic light movement to really show off what we can do with this technique. So let's go ahead and see what we can do about that. So looking at our light map here, you can definitely see some kind of haloing happening in the area which would be the back wall here. And since that area is not being affected much by our light, especially in the final composite here, we might as well just make it so that it isn't affecting it at all. And that way we get rid of those areas. And luckily we have a handy dandy utility here that can help us with that. It's our depth map that we spent so much time and hard work generating. We can just do the same thing that we did with the fog or the mattes technique that we looked at, and just multiply our light map by the depth map. And of course we'll have to put this before the shuffle, before it gets shuffled into the alpha channel. And in order to make sure that we're not boosting up the front values, I'm going to put a grade node here and go ahead and white clamp, and then we can adjust the black point to knock out our back wall area. And you can see with that addition, we are no longer getting such a halo around our character. In fact, you can see we are pretty much just affecting the foreground here, looking pretty good, I would say. And now, in order to get that dynamic movement, I'm going to go into the light here, and we're going to need to animate the position of it. And we could do that with keyframes, but I'm going to use a little expression to make it neat and tidy. And so we'll notice that our X value here is currently at negative 0.18, and we want to animate it from negative 0.18 to positive 0.18. So I'm going to use a sine function to give it that sinusoidal motion. We'll say sine of the frame divided by, let's say, 5. So that means we're using the frame number to drive the sort of evolution of our sine function, and the divided by 5 is just a sort of speed control number. So we'll put the closing parenthesis on, and then we'll need to multiply it by 0.18 in order to get it to go from negative 0.18 to positive 0. And if I do this, let's just do a little flip book, and we'll see what the result is. And here is our result. So I'd say this is looking pretty cool. Of course, there are, a few more issues that we can look at here, but we've got some very nice dynamic lighting going on in our shot just from this depth map project that we've been working on. So let's take a look at cleaning up the final few bugs here. The first we'll notice is that we've got this noise going on around the edges. We've also got some nasty looking negative holes going on, which isn't something that we want. And finally, there is just a little bit of flickering happening on some of the character here that we should be able to clean up. So let's go ahead and do that. We want to look at a frame that has a bunch of that noise that we're trying to get rid of. I think there was something around here. Here we've got some of that noise, and we can also see there's some areas that are getting super dark. If we look at our light map output from guided blur, see what we're getting here are actually some negative values in the alpha channel. If you look down here, see negative values, and we don't want those. So in order to get rid of those, I'm just going to place a clamp down after our guided blur, like this. And now we should be getting a little bit better of a result. You'll see that this isn't so bad anymore. We also probably want to disable the maximum clamp so that we're still getting our full range of brightness increase. So that's looking better. Of course, there still is some noise. And you'll also notice that some of the spots on the floor are looking a little weird. You'll see the texture kind of gets removed from the floor in some places, and that's a bit of a weird result. Maybe we don't want that to happen. So an easy fix for that is to use a median node. It's sort of like a blur, but it preserves the edges. So if I put this here and set the channels to alpha, what we get is this. So we're kind of removing a layer of fine detail here. And because all that noise and the adjustments to the floor that we're flattening it out kind of are in that fine detail sort of spectrum, if we use a median to knock that out, we should be getting rid of a lot of that noise. That is looking quite a bit better, and we're getting some of the floor detail back in here. It's just what I always wanted. We increase the median size a little bit, we can bring that up a bit more. So that is mostly everything fixed, but I did just want to say it was a little hard to see in the clip, but there is some flickering going on, primarily in his chest, our character's chest. And you might recall that in the previous tutorial, I mentioned that the blur size on this guided blur up here was essentially a control for how much of the original flickering gets passed through to our final output. With a blur size of 150, it's a pretty good result. It looks like this. And it's not bad at all. But, any flickering that's happening in this depth map is going to get passed into our 3D render, and as such will show up as flickering in the final result. So I'm going to, switch our color transfer from this prepackaged render that we did over to our raw node output here, and then reduce this guided blur all the way down to maybe 70, blur size of 70. And what we'll see in the result is that it won't be an obvious change that we're getting in the image, but we will see that the actual result that we get is going to be a little bit smoother. So let's do one more flip book and we'll see what our result looks like. And the result is this. And folks, of course, there's always things that we could do to clean this up further, maybe touch by touch, just a little bit more here and there, but I think that this does a great job at giving you an idea of what is possible with this technique. We have generated a depth map used it to recreate the scene geometry, and then used that to relight the shot, adding some brand new interactive dynamic lighting to a shot that even has a moving character in it. Moving camera, moving character, all that. And with that, I just want to say thank you, dear viewer, for watching this video, watching this tutorial series, and following along with me. If you haven't got them already, once again, the resources are in the description. I hope you've learned something interesting from this and taken away some techniques you can use in your own projects, because this depth map generation technique is applicable to so much more than what I've showcased in this video. And if you discover any cool techniques, I'd love to see them in the comments. If you're there, might as well drop a like and a subscribe as well. I want to give a big thank you to the Foundry for having me here on their channel, and you can find me over at nodesaren'tscary.com. My name is Julian Kreusser, and I'll see you around.